Is the recording on? Ajay?
Yes, sir.
Yes, sir.
Yes.
Okay. Yeah. So, yeah, yesterday we had some problem with the conversion of bases. It's quite straightforward actually. So here a number in B1 in base 1 is to be converted to base 2. All right. And it is to be of the form A dot B, where dot is the uh, is the separation between the integer part and the fractional part. Okay, so you can express, so in the NB1 is in base 1 and you want it in base 2 as shown over there. So in base 2 its evaluation is shown over there. So that A part you can you can just, if you multiply by B2, then you find that you get A0. Yeah, so if you factorize B2 from the other part, then you get A0. So basically the integer part of the number in base 1 in base B1, you just divide that by B2 and you take the remainder. So that gives you the least significant digit of A B2 when you divide A by B2. Okay. So that is the basic step. I mean, you're aware of it, but it was not properly presented yesterday. So, and uh, and that's how you go on. So it's if that A dash, uh, that part, that's a quotient actually. So if that turns out to be 0, then you are done. Otherwise, you carry on in the same way. So you get the again you take the remainder and get the next significant digit and so on. So that is the integer part. And so far as the fractional part is concerned, so there you find that if you multiply b by b2, then you get a minus 1. Okay. So basically that fractional part of NB1 you multiply by B2 and so that will give you the first digit of the first digit after the fraction. Okay. uh, and uh, and the remaining part b dash, if b dash turns out to be 0, you terminate, otherwise you carry on in the same way to get the later digits of the fractional part. So that is the procedure. Uh, yeah, so I've just put
Excuse
it
me, sir.
together. So I hope this is okay. Do you have any questions regarding this part?
Excuse me, sir.
Yeah,
Sir, this conversion is it applicable for any
yeah.
means?
This is general. This is general, as you can see. It is
Yes, sir.
general. All right. Now, uh, yeah, and then the other part, that is, you can also do a direct evaluation if arithmetic in base 2 is convenient. So that is what we have been doing actually. You can also do a direct evaluation. So these examples we covered yesterday. So these are the same examples, and that, one second. What is that? Oh, I don't know what happened. I had, anyway. Uh, oh, sorry. Yeah, this is the direct evaluation. All right. So, so this is what we have been doing, and this is the last example we did to convert a number in base 10 to base 12. You can, I mean, direct evaluation can work. If the arithmetic is convenient, I mean, the last example, it is not that convenient, but it can be done. So, yeah. All right. So this is basically just we're revisiting what was done yesterday and to correct some errors. Any questions there? Okay. So I think, yeah, Pavitra, do you want to take over now? Hello.
Sir, you are muted.
Yeah, I know. Just a minute. Yeah. Okay, so Professor Pavitra Mitra will take over now. Okay, yeah, I'll stop sharing.
Okay, so maybe I'll share my screen. Okay, so I think, okay, by the way, am I audible? Anybody confirm?
Yes.
Yes.
Okay, thank you.
Yes.
Thank you. So see, so far we have seen representation of numbers in various radixes, various bases. So this is what we say a radix-based number system, and you basically. So one of the particular radix-based number system we are interested in this course. There are two actually. One is the decimal, and the other is the binary. And we have seen that, okay, I mean, each of them are base 10 and base 2, so that's all fine. But what happens in practice is that, so these bits which you used to represent, okay, if you take a binary system, you also get a string of bits to represent numbers. But what people did was they sometimes used a bit string which is slightly or little bit modified from the usual radix-based system. They are still, I mean, they are similar, but not exactly binary or not exactly decimal. They shifted from some representations because of some advantages, maybe because of implementation advantages or something. And such bit representations would be called a code. Okay, so one of the common thing that you'd like to have a code for are numbers, decimal numbers. Okay, so you have decimal numbers or you have digits of decimal numbers from 0 to 9, and you have to have bit codes for them. So that's represented. In fact, that's completely your choice how you'd like to represent. Okay, they will have some similarity with the corresponding binary radix system representation, but it's up to you. I mean, it's up to your advantages what you feel should be the representation. Okay, so people came up with several such codes, several such codes of representing decimals using bit strings. So one of the most popular representation is something called a binary coded decimal. Okay, so what is done in a binary coded decimal is that you have a decimal number, say 2022. For every digit of the decimal number, you have 4 bits allocated to it. So sometimes called a nibble, basically half a byte. So you have 4 bits dedicated to every digit of the decimal number. So you have, so if you suppose you want to represent 2022, basically you would need 16 bits to represent 22. I mean 4 sets of 4 bits to represent 4-digit decimal number.
Yeah, just 1 minute, Pavitra. Yeah, so I would like to put a question to the students that can you just suggest why this binary coded decimal was introduced? I mean, it is you can just think and try to answer. Anyone?
So
Why?
it's
Why? Yeah.
fast to read.
Yeah, so the reason is actually quite simple. See, ultimately, people have to use the data. Computer will compute something, but at the end of the day, people will have to use those results. So for people, people are used to the decimal number system. Okay. So, so when the inputs are taken or when outputs are given, it is convenient to exchange information in decimal. But the computer works in binary. So a simple mechanism would be to just have the binary representation of each digit. In fact, that is exactly what is binary coded decimal. So as Professor Mitra was saying, say 2022 or something he was saying. So 2022 you have the 4-bit representation of 2, 4-bit representation of 0, and again the 4-bit representation of 2 repeated twice. So it is easy to code. Okay, it's easy to code.
Yeah.
So the challenge is how you do arithmetic with such numbers and how you convert between binary to BCD. So so as you might expect, uh, inside the computer, the arithmetic would be simpler in binary. So so BCD is kind of restricted to input output. So you can input the number in BCD or you can display the number in BCD, but internally you'd like to work in binary, because as we shall see in later classes that the arithmetic is much easier when you handle the information, the numerical information in binary. But then there is a question of converting between binary to BCD. So we'll be looking at that. I mean, that's a interesting conversion. So the more efficient method we'll see a little later, but a basic mechanism will be covered now. Yeah, okay.
Okay. Okay. Thank you, CRM, for this. So, so that's precisely the purpose. You want to, in fact, some of the earliest computer like IBM 360 and VAX, they used a BCD representation internally also. And many of the calculators that you have used, they use a BCD representation because that's most of the time you display it. But anyway, okay. So let's see what does this mean. So as we have discussed that every digit of decimal has 4 bits to represent the decimal. Okay, so now since there are 4 bits, you kind of have a redundancy because you have 16 different combinations of 4 bits. So there is a name for this. Each of these 16 different combinations are called tetrads. They are called tetrads. And using these 16 different combination, you want to represent 10 binary digits. 0 to 9, you want to represent 10 binary digits. Okay,
Decimal
so now,
digit.
10 decimal digits. You want to represent 10 decimal digits, 0 to 9. So you have 16 places which you can use, and you have 10 things to represent. So depending on which of this tetrad you use to represent which decimal digit, that's your choice. And people have tried out different things. So the simplest possibility is something called a BCD 8421. It's kind of a positional system. So the first bit has a weight of 8, the second bit, usual binary, the second bit has a weight of 4, 2, and 1. So it's 8421. So if you have this 8421 representation, then the 0 to 9 in binary, so 0 to 9 are identical for binary and BCD. 0 to 9 are identical. For remaining bits, they are unused. You may not use them. In fact, let me show a quick picture that will maybe make things a little more better. Okay, so this is a picture. So this is these are the tetrads. So 0 0 0 0 0 0 0 0 0 0 0 0 0 1. These are the 16 tetrads, right? And as you can see that from least significant 1 to most significant 8, you have the weights for each of these positions of the each of these bits of the tetrad. So bit 1, bit 2, bit 3, bit 4. Okay, and now now the thing is, if you want to a simple 8421 BCD would do it like this. So this is 8421 BCD. So this 8421 BCD 0 to 9, these are filled up. These are filled up. So what I am trying to do is that I am trying to map these 16 different tetrads to 0 to 9 decimal digits. I'm trying to map them. So the blue boxes are the ones that are used. The gray boxes are the ones that are not used. And I have listed here the decimal numbers 0 to 15. So simple 8421, simple 8421. So the first 10 digits will be used. First 10 digits will be used. Okay, you need not restrict yourself to this 8421 weight. You can use some other weight also. Okay, so first, for example, the fourth bit, it can be 7 and rest can be 421. You can also have a 7421 BCD. So if you use a 7421 BCD, you will see these will be the mappings. Okay, so the first tetrad would be 0, the second tetrad would be 1, and so on. The sixth tetrad would be 6, but the seventh tetrad is not 7. The eighth tetrad is 7. So this is some, there are other examples. This is something called a ICANN code. In some of the earliest VAX computers, they were used. So you have 0, 1, 2, 3, 4 for the first 5 tetrads. And then rest of the tetrads are unused. Again, 5, 6, 7, 8, 9 are used. And then you have a XS3, which you see is basically 8421, this BCD, shifted by 3. Shifted by 3. Okay, it is shifted by 3. Okay, in fact, you can show that you can actually attach weights. You can attach weight. In fact, this would be -3, 2, 1. Other type of weights you can attach to it. Similarly, you can have XS6. You can have jump codes. You have 0, 1, then you jump, and then you represent 2, 3, 4, 5, 9. You have jump 2, jump 8. Okay, this type of codes are possible. This type of codes are possible. Similarly, you can basically change your weights also. So this is a 4221 BCD. The fourth bit has a weight of 4, and so on. In fact, for that matter, you can have negative weights also. You can have negative weights also. We'll give example of negative weights. Right. So this is what is used. People used many other strange combinations also. For example, there is something called a magnetic tape code, which is something like this. So the 0 tetrad, all 0 tetrad is not used because that's difficult to detect in a magnetic tape. Okay, so other possible combinations are also there. So I think the idea is simple. Basically, the idea is you have 16 tetrads and you have 9 numbers to represent, and you have to basically map which tetrad will represent which digit in decimal. The most common thing is something called a 8421 BCD. So the first 10 are used. So sorry, not 9, 10 decimal digits you have to represent. So the first 10 are used. Okay, but that's not the only possibility. You can have other things as well. Okay, so let's see. So, all right, so now the next question is, okay, single digit decimal you have represented using 4 bits. What about if you have decimals which are greater than 9? Say, what about decimal values 10 to 15? What is their BCD representation? I mean, what you have to do to do such BCD representation is the following. You look at this rule. So if D is from 0 to 9, fine. You just get the binary number for that, 4-bit binary number for that. If D is greater than 9, you add 6 and take mod 16. Okay, you add 6 to D. So if your number is 10, you would add 6 and take mod 16, which is 0. If you have 12, you would add 18, mod 16 is 2. Okay, and for that, you will represent so let's take this. So basically now that it has exceeded 9, you will need not a single nibble, you will need 2 nibbles to represent it. Okay, you will need 2 nibbles to represent it. There will be overflow. You cannot represent it using this thing. So
Sir,
yeah.
sir, can you show this with the example, sir? I didn't get this.
Okay, let us take this example. Say D is 12. Okay, D is 12. So what is 12 in binary?
Just a minute. Yeah, so just think that you got two numbers, say 6 and 4. No, say 6 and 6. Okay. So suppose you add the two, your result will be 12, right? Now 12 can be accommodated in 16 bits. So your result is 12, but 12 is not directly, you can't directly represent 12 in binary. Although you have got 12 in the 16 bits, you cannot represent 12 directly in binary. So basically, the binary 12 has to be made into decimal 12. Okay, so that is what is being explained. All right.
Yeah. So let's take this example, D equal to 12. So what we will do, we'll add first 6 to it. You get 18 and mod 16 is 2. Okay, so 2 is 1, it goes to the next higher place. So let us think of it like this. So D is 12. So the binary for D is 1100. Okay, and you add 6 to it. That means add 0100 to it. Okay, this is 6, this is 6, this is 6, and this is 12, both in binary.
Yeah, just 1 minute. Yeah, so how do you compute mod 16? Is it easy? I mean, because after all, these operations must be done fast. So anyone can tell how to compute mod 16?
Take right most 4 bytes.
Yeah, so it is actually trivial. Mod 16 is trivial. So, as you can see, I mean, when you carry out this addition, this is exactly what you are left with. The last or the for least 4 bits, those are that is what you have when you take the remainder on dividing by 16. So when you are working with binary numbers, taking the modulo 2 to the power any exponent of 2 is quite easy. All right, yeah, thanks.
Yeah, please.
Like here, D plus 6 mod 16, we are essentially doing D mod 10, but we are doing this because it is easier to do. Right?
No. The arithmetic is, see, when you add 6, what you are left with mod 16 is the lower digit, which is in this case say 2 of 12. And you have a carry which goes to the next higher place of the BCD. Yeah.
Exactly. I think he is in some sense correct, because if it is if the mod is 2 to the power something, it is easier. So we don't want to take mod 10. Mod 16 is easier to take. In some sense, he is correct.
We are because see, you have to understand that the addition is happening in binary. For example, when you add 6 and 6, the result that you get is actually 12.
Yes.
All right. So yeah, okay. So that mod 10, yeah, that is right. So that yeah, the remainder on 10, that is division by 10 is not easy. But as you can see, if you add 6 and take the remainder after adding remainder on division by 16, that's easier. Yeah. So
basically, CRM, do you mean to say that this is because of the fact that A mod 10 is A plus 6 mod 16?
Yeah. I mean, that is what is happening. For 4 bits.
Yeah, and since we prefer to take mod 16, we'll add 6. That's why we'll add 6. And then take the mod. Okay, so this is fine. But as you can see that actually from a implementation point of view, this requires a number of steps. First you have to add 6, then you have to drop the most significant bit. So this requires, you can actually have faster ways or faster algorithms to do this conversion from binary to BCD. You have faster ways to convert from binary to BCD. In fact, what we will do is that maybe we'll delay this discussion a little bit. There is a nice algorithm called the double algorithm. We are not, it consists of addition and then shifting. Only shifting. I think it can be done in only shifting. So we'll not do that. It's a bit involved algorithm. We will maybe discuss it in the next class. But first let us complete this discussion. These examples we'll do later. Okay, let us complete this discussion on these different codes you can have. All right, so we'll mainly, so you see that BCD is one example where you are converting decimal to binary digits. There can be many other codes possible. There are two class of codes are very important. One class of code is called a weighted code. So weighted code, basically you have 4 bits and there is a weight attached to every bit. There is a weight attached to every bit. And to get the decimal number, you basically multiply these values of these bits with the weights of that bit. So you can easily see, for example, if the weight are 8, 4, 2, and 1, so this number would be 1 into 1 plus 2 into 1 plus 0 into 4 plus 0 into 8. So you have to just multiply. So this formula you have to apply. You have to multiply by the weight Wi with the bit value xi and then add up over all the bits. Okay. All right.
Sir, can you please once show the previous slide?
That this BCD
12
representation.
12
Yeah,
sir.
please. Yeah, sure. Let me come to it. This one?
Yes, sir. Got it, sir. Thank you, sir.
Okay. Okay. All right. So let us come to so these are so this is a class of codes which we call weighted codes. You can have different weights. Like for example, you can have a weight of 2, 4, 2, 1. You can also have negative weight 6, 4, 2, minus 3. There are two properties of this code which we'll study. First thing is that we'll study what is called a self-complementing code. Self-complementing code means, by the way, these binary strings, we'd call them as code words. We'll call them as code words. Okay, so what is a self-complementing code? If you take a number, a decimal number, and take its tens complement, and if you add these two, you will get 16. So here is and this is what you will get. Okay, this is what we'll get. So you take a number, take its 10 complement, forget about this plus 3, you will get 15. Sorry, you will get 15. So that's kind of that is something called a self-complementing code. It can be shown, maybe you can take it as an exercise. If sum of these weights Wi is 9, then it's a self-complementing code. Okay, if the sum of the weights is 9, for example, 8421 is not a self-complementing code. It's not a self-complementing code. Okay, so what will happen in a self-complementing code is that if you flip the bits, you just flip the bits, you get its tens complement. So you can easily get the tens complement just by flipping the bit. Okay, so it can be shown that will happen only when, yeah.
So by flipping the bits, won't we get the nines complement?
Sorry, nines complement, not the tens complement. We'll get the nines.
Also, like in the 2421 weights, the 5, the representation of 5 is 1001. How is that happening?
Representation of 5, maybe this is a mistake.
Sir,
Wait.
there
One
would be two representations, sir.
There is 2 representation of 5, but I'm
Plus
just
2 plus
checking.
1 and
So
4
it
plus 1.
should be like 1011 because that's the one that's complement of 4.
So this is 1011 is one representation of 5, and 0101 is another representation of 5.
Sir, so how to how to choose which is the best and which is not the correct one?
See, the thing is, it's not a question of which is best. I mean, you can, so that's how it is. You can have 2 representations of 5. Both are treated as 5.
and both also complement as 4.
Let's check that. If both complement as 4. Let's check that. So
Yes, they both do. One
they
is
both do.
the
Four
one
also has two
we
representations.
written, or the one is 1010, which is 2 plus 2,
Right.
4.
So both of them complement to 4. Both of them complement to 4. So maybe you can try this as an exercise. If the sum of the weight is 9, then it has to be a self-complementing code.
Yes, for
Why?
0, it will obviously be all zeros. And if the sum of it is 9, then for 9, it will be all ones. And then there are 9's complements of each other.
What about the rest of the digits?
For the rest of the digits, whenever we flip one, let's say we flip any of the values from 0 to 1, then for the complement we'll obviously be subtracting the same number, so the sum is unaltered.
Right. Good. Good. That's a nice clue. Okay, so these are you can have other weights as well, but as we have said that okay, it's preferable to have. But I mean, again, see, I would not say what is preferable and what is not preferable. It depends on the situation. Some codes have some advantage because some people, when they designed their digital system, some of the operations are very common and they wanted to minimize that circuit. That's why they went for this type of code. So there are many people which use different type of codes. Okay, so the codes may be unweighted also. That means you need not have a fixed weight associated with all these 4 bits. They may not be a fixed set of weights. You can have different set of weight. One example of this unweighted codes is something known as a XS3 code. Okay, so how do you get a XS3 code? Basically, you add binary 3 to the corresponding BCD 8421 code. You take the 8421 code. So if 0000 is the representation of 0 in BCD, the XS3 representation would be 0011 and so on. You just add 11 to it, 0011 to it. Okay, so basically everything is shifted. Everything is shifted. If you remember this picture, let me come back to this picture. If you see this picture, you see everything is just shifted. Everything is shifted by 3 bits. Okay, so that's easy to do. Basically, you have to add
Sir,
0011.
In that representation that you showed just now, all those different ways of representing are just arbitrary, right?
They are
They're
arbitrary. They are designer's choice.
Okay, yes.
Each of them have their advantages and disadvantages.
Yes.
So
Okay.
this was, see, I'll tell you, see, this was when computers was just being built, say from this very early generations of computer. So their circuits were not like this dense IC chips and such things. They had, it was really important for them to optimize the circuit elements, number of gates and everything they use. So every possible operation that they frequently did, they adopted their own code so that the circuit becomes simpler or faster. So that's why people comes up with. So there are things like, have you ever seen something like a barcode? So optical. So you must have seen that many of the big bazaars and anything, there is a strips added to the products, and there's an optical scanner which reads it. So there is a number. It actually represents a very large number. which represents the product code or something. In fact, not one number, it represents 3 numbers, and they have a particular coding scheme. So the nature of that bar represents what value it is. So there are 2 kinds of bars, like there is a white bar and a black bar. So I think it's the reverse. The white represents 1 and the bar represents 0, something like that. And that's a coding also. That's a valid coding. And there are requirements why they have taken such a coding. So there are maybe requirements like some of the operation is fast. There are even requirements like it has to be fault tolerant. So when you are reading using an optical scanner, maybe there is fault in 1 or 2. So you have to do something that these faults do not disrupt the actual value intended. So there are many things, many considerations that are given. So there is another code which is kind of a cyclic code. There is a cyclic code. So you see, like this is the representation. I'll not say anymore. You see what basically happens is that you see this so there is another code called a gray code. This is cyclic as well as some properties. One of the property you see that every 2 such strings differ by only 1 bit. Every 2 corresponding, consecutive strings, they differ by only 1 bit. They differ by only 1 bit, 2 consecutive strings. Okay. So, for example, you are reading the number 7 and one of the bit is corrupted. You will at most read 6 or 8. You will not make an error more than that. You will either read 7 as 6 or 7 as 8. That's a small. You are not reading 7 as 1 or 2. Whereas here there is a possibility. If some of the bits get corrupted, that may happen. Okay. So this kind of property is another nice property. So these are more robust to bit failures and such thing. There is another very important code called a gray code. I'll explain what it is and I'll tell you how to do it. Okay, so you can see all these 3 codes, XS3. Yeah.
Sir, in the cyclic code, the representation of 5.
Okay, that thing I mixed. Yes. So many of these weighted codes and unweighted codes, you can have actually multiple representations of the same number. So what happens is that many times it happens that there are 2 versions of XS3 code. Okay, so one group of people maybe will choose one of the representations of 5 as their convention. Maybe another set of people will use the other representation of 5 as their convention, or maybe they live with both. Okay, so depending on what this mapping is, they can actually, let me see if I have a picture of that.
No, sir, I meant if the 3rd bit of 5 gets corrupted, then it will vary greatly, right? It will move on to 8, I guess.
5 will go to 8. Let me check.
Yes, sir.
5 will go to 8. Wait. Yeah, that's a problem. Yeah, maybe.
Also, 4 will get to 9. The 3rd bit.
4 will get to 9. Yes. So okay, I retract my statement. So usually that, I mean, there are cases where that will not happen. In fact, let me postpone the discussion. These codes are called error correcting codes. We'll come to that discussion later. Okay, let me have a proper mathematical discussion, so we'll come to that.
One doubt in cyclic, like is it compulsory to start flipping the bits from the rightmost bit, or like we can represent 1 as like 1 and then 3 zeros?
Is that cyclic?
Means 0 is 4 zeros, and the next number 1 we can write as 1 and then 3 zeros. Like it is only.
Okay, and what about the next number?
Like then we can start writing shifting to the right. Means whatever.
Okay, yeah, I think that's also a valid cyclic code. That's also a valid cyclic code. But your corresponding mapping to decimal, that will change maybe.
Yes, sir.
That will change. Okay, so another possible exercise you can do is that, so we have obtained this XS3 by adding 3 to the BCD 8421 BCD code. There exists a weight for XS3 also. Can you figure out what is the weight, positional weight that is used in XS3? There exists a weight also. That also can be figured out. So that also I leave it to you as an exercise. What is the weight used in XS3? Okay, so let us look at this. Let us look at these things. So this is a property of the cyclic code, but you have pointed out a problem with that. I'll clarify that. I'm not entirely sure now. Maybe in the next class I'll clarify that. What happens?
Sir, can you once again explain what is exactly meant by self-complementing? Like, I am confused in it.
Okay, so you flip every bit. You flip every bit, and the decimal number that corresponds to those transformed bits is 9 minus the original number. Okay, is 9 minus the original number. So see, what does that mean? What does this mean? So if n is your number, so this I'm showing for the XS3 code. If n is a number, so n plus 9 minus n should add to 16, should add to 15. N plus 9 minus n should add to 15. So in general for BCD, this will not hold. In general for BCD representation, this will not hold. Okay, but if you take the XS3, this will hold. You take XS3, this will hold.
Sir, I could not understand how we are deciding which combinations to choose for which numbers in the cyclic and gray systems. Like
gray, I'll explain. Gray, I'll explain. Cyclic, so I have written them down sequentially. This is 0, 1, 2, 3, like that.
Like, how do we decide? They don't seem to follow any pattern in cyclic.
Okay, let me explain the gray code. It will become clear. Let me explain the gray code.
Sir, so for self-complementing, what you are saying is that take the binary, means for a particular representation is self-complementing if we write that representation for n and 9 minus n, and if we add the two, then we get 15.
Right, you get 15.
Okay, sir.
Okay, so so cyclic, we have told that two consecutive representations will differ by only one bit. We'll talk about another type of bit, which is a reflected code. Reflected code means how many are there? If you take this, for example, if you take the gray code, and let me see if I have more gray codes available with me. Yeah, this is the gray code. Okay, so this is the numbers. I have just represented 0 to 7, 8 numbers. You see that if you drop the fourth bit, remaining 3 bits are reflected versions across this line. Remaining 3 bits are reflected version across this line. Okay, understood. So if you divide, so I have written down gray codes from 0 for the numbers 0 to 15. I have written down 16 gray codes. These are the corresponding binary codes. So if you look at the first bit, you see for the first 8 they are all 0. Next 8 they are all 1. So and the remaining 3 bits, you see they are just reflected version. Okay, so tell me one thing. So suppose I give you the first 8 gray codes. Can you construct the next 8 gray codes? If I give you the first 8 gray code, how will you construct the next 8 gray code?
Sir, I will reflect and then
I'll reflect the last 3 digits, last 3 bits, and I'll write 1 in the first position. And this I can recursively do. So look at this. So let's start this way. Okay, let's start this way. So 0, 1, then this is first position. For every 2 numbers I'll reflect. So 0, 1, then I'll write 1, 0. Then again I'll reflect 0, 1. Then again I'll write 1, 0. So this way I get a. In fact, I need not construct this last 4 also. Say I take 0, 1 and I take 1, 0. Fine. So I stop here. Okay. Then what I do, this 0, 1, 1, 0, I reflect again. I reflect. Do I need to reflect? Wait a minute. So this will also get reflected. So what? Yeah, good. Fine. So I take 0, 1. I take 0, 1 and I write 0, 0, 1. Okay. So from 0, 1, how will I extend 1 bit? Can anybody tell? From 0, 1, how will I extend 1 more bit? I take 0, 1, I reflect it and add 1, 1. So this much part I get. This much part I get. Okay. How do I expand 1 more digit? This entire thing I reflect again and then add 1, 1 here. Okay. Then do you get the point? Is there any doubt we have? So what we will do is that we will take 0, 1. First I'll just write 0 and 1 in the first position. Okay. And 0, 0 in the next position. I'll just reflect it to get 1, 0 and write 1, 1 here. So now these 4 2-bit numbers I have. I'll reflect these 4 numbers to get 8. In the first 4 position, I'll put 0. Next 4 position, I'll put 1. So I have these 8 numbers now. So these 8 numbers I'll reflect. First 8 I'll put 0. Next 8 I'll put 1. So now I have 16 gray codes. So if I have to increase it to a 5-bit gray code, what will I do? If I want to expand it to 5-bit gray code, what will I do?
So we will reflect the entire thing, add a 0
Yes.
to the first 16 and add 1 to the last 16.
Very good, correct. That's the idea. And is it cyclic? That means does 2 consecutive numbers differ by only 1 bit?
Yes, sir.
It is cyclic. It is self-reflecting as well as it is cyclic. Okay, it is self-reflecting as well as it is cyclic. Okay, we'll see that this has several advantages. Okay, so now to construct this gray code, so I have kind of given a visual rule of constructing this, but actually you have to write logical rules so that you can build a circuit to convert binary to gray and vice versa, gray to binary. Okay, so it can be shown. I don't think I'll do it today. It can be shown that you can use a number of XOR gates to do this conversion from gray to binary and binary to gray. Okay, you can do a number of bitwise complement and XOR operations to do this. Okay, so maybe I'll stop here today. I will come to this conversion and then I'll come to other questions, that what are the weights for gray code and other cyclic codes. Okay, all right, thank you.
Sir, slides.
Sir,
Slides is not updated. Okay, I am calling CRM right now and doing it.
Sir, I have a doubt in the BCD.
Wait, let me share again.